So linear operators, solution of linear operator is very general and has many applications. So it is known as linear map, linear mapping, linear transformation, linear function. So these are different names by which it goes. So basically, what is it? What is a linear operator? So when we talk about a function f is a mapping from a set A to a set B, right? So there's this one element in a set A. There's a set A and there's a set B where A is called the domain, B is called the codomain. And the function f takes a value from A and maps it in B, right? So that was my function f. All right, so this function f is defined on some domain A and codomain B. If this A happens to be some vector space V, and if this B happens to be some vector space W, then this function is known as a linear transformation or linear operator. So V and W, when they are different linear spaces, in that case, we get this function as a linear transformation. Okay, so what are examples of vector spaces? So vector spaces could be, let's say, R square vector spaces. R square is a vector space. R cube is a vector space. 2 cross 2 matrices is a vector space, right? So 2 cross 2 matrices is a vector space. 2 cross 3 matrices is a vector space. So vector space could be different connotations. You can take any of them as your A, any of them as your B. So suppose R cube is your A and this 2 cross 3 matrix is your B. Hello? Yes. Yeah. So suppose R square is your A or vector space B, and this is your 2 cross 3 matrices. So my function f, which is a linear operator, is basically just a matrix which, when multiplied to an element x belonging to R square, will give me an element y belonging to this 2 cross 3, such that f times x is equals to 1 for all x belonging to V and y belonging to W. Remember, W is 2 cross 3, V is R square. So f times x is equals to V. So that is the idea of a linear operator, that when you multiply this linear operator with f, then it's going to give me y. Right. So this x is coming from R square. So R square is represented in this format. So it's going to be a 2 cross 1 matrix. Right. And this is, okay, I should have taken R. Okay, I should have taken R cube actually. Not even R cube. Let's say I take x as 1 cross 3 matrices. 1 cross 3 matrices can also be represented in R cube. So suppose I represent x as 1 cross 3. I write them as row vectors. So 1 cross 3. And y is my 2 cross 3. So what should be the dimension of this f? If f is a matrix, what should be the dimension of f?
2 cross 1.
2 cross 1, perfect. Okay, because 2 cross 1 times 1 cross 3 is going to give me 2 cross 3. So the beauty of linear operators is that linear operators, they satisfy this very nice property that the function can always be represented as a matrix multiplication. That is a property of linear operators. It's a property that we are not going to prove. See, otherwise we do not have such good properties, right? So suppose you define a general function, f of x equals to x squared. Okay. So for this function, I know that f of 1 is equals to 1, f of 2 is equals to 4, f of 3 is equals to 9, and so on. But I cannot find any matrix f such that f into 1 should be equal to 1, f into 2 should be equal to 4, f into 3 must be equal to 9. I cannot find a constant f which satisfies all these equations, all these infinite equations. There are infinite such equations, right? Because this f of x equals to x square is satisfied for all x square, even non-whole numbers. I cannot find any constant matrix or real number f which satisfies this equation, right? But here I can find such a matrix f which satisfies this equation for all x and y pairs. Okay, for all x and y pairs, this equation will be satisfied for a matrix multiplication. So now application of this function is nothing but the multiplication of some matrix. So that's the beauty. So there's some properties of linear operators which we need to know. The first property is if you take any two vectors in the domain, then f of x plus y will be equals to f of x plus f of y. So this is true also because we are going to look at linear operators as matrix multiplication. So if you consider f, x, and y as matrices, then obviously this property is true. And for all x belonging to vector space and y, and for all lambda belonging to R, f times lambda x must be equals to lambda times fx. So this is again a property of matrix multiplication. So now your linear operators will follow all those properties which matrix multiplication follows. Right. So this is not going to be a statement we are going to prove, by the way, that linear operators are going to follow this matrix multiplication, that linear transformations are basically needed, a multiplication of some matrices. But it is something which you are going to consider as true in general, because that's in the hindsight, it's going to make your job easier if you are dealing with questions related to linear transformation. They are rare. Like you can expect one of the exams to ask these questions in a given year. So on an expected level, DSE, ISAC, JNU all combined, IGIDR, if you combine all of them, one of the exams will ask a question based on linear operators. But when they do it, they are pretty easy ones. So that's why we are training for them. They are low hanging fruits. Okay. So F preserves the operations of vector addition and scalar multiplication. Below we discuss several examples of mapping which are or are not linear operators. So f of x equals to cx. So this is a linear function. All right. So is this a linear operator or not? So how do I check if something is a linear operator? So suppose I'm given this function f of x equals to c times x. Okay, so I need my linear operator to satisfy those two properties. What are the two properties? The properties are one, f of x plus y should be equals to f of x plus f of y. And the second property is f of lambda x must be equals to lambda times f of x. So let us see if this function satisfies this property. Right, so property one would be f of x plus y is equals to c times x plus y, which is basically cx plus cy. Now cx is f of x and cy is f of y. So it satisfies property number one. Property number two is f of lambda x is equals to lambda times, so f of is equals to c times lambda x, which is lambda times cx, and cx I know is basically f of x, so this is lambda times f of x. So f of lambda x is equals to lambda f of x. So this is also true. So both these properties are true. So this thing is a linear transformation. Now let us look at another function f of x equals to x squared. So when I look at this function, f of x plus y will be equals to x plus y whole square, which is x square plus y square plus 2xy. Right? Now this thing is f of x and this thing is f of y and this thing is extra. So this thing is not equal to f of x plus f of y. Right, so even if one of the properties is not satisfied, then this thing is not a linear operator. So this thing is not a linear operator. Now, f of x equals to x plus 1. Will this be a linear operator or not? What do you guys tell? What do you guys say? F of x equals to x plus 1. Is this a linear operator or not? Oh, it's not so difficult.
No, sir.
No, right. Why? Which property is not satisfied? 1 or 2?
1 is not satisfied.
1 itself is not satisfied because f of 1 is not, because f of x plus y will be equals to x plus y plus 1. On the other hand, f of x plus f of y will be equal to x plus 1 plus y plus 1. So that is equals to x plus y plus 2. Right? So property 1 itself is not satisfied. I don't even need to go to property number 2. So that's why this is not a linear operator. So in subsequent sections, we'll see how differentiation is a linear operator, how integration is also a linear operator. Now, expectations is also a linear operator. So expectations is something that we have not done. We will do it in the next section, next chapter, that is probability theory. So in there, we will look at what are expectations, what is the expectation function. So expectations also satisfy these two equations. Expectation of random variable x plus y is expectation x plus expectation y, and expectation of lambda x is equals to lambda times expectation of x. So that's why this is also a linear operator. So whatever property linear operators follow, those properties, expectations will follow. And expectations are a big deal for economists and statisticians alike. Expectations are big things. So these are some things, these are some things we'll look. 4 and 5. 6 is something which is pretty obvious once you know what is expectation function. Now, a function defined as in this format that f of x comma y is equals to y comma x is a linear operator of symmetry with respect to bisector line of the first quadrant. What does this function tell you? F of x comma y is equals to y comma x. It's basically that if you give me as input some number, let's say 1 comma 2, the output will come out to be 2 comma 1. It will invert the x and y coordinates. So if you look at the R square plane, what's happening is that if you give me any point like here, 2 comma 1 or 3 comma 1, let's say, the output will come out as 1 comma 3, which is like an image, if you keep a mirror along the x equals to y line, this 1, 3 will be like an image of 3, 1 along this mirror. Okay, it will be an image along this mirror. So this particular function or this particular transformation is known as image along y equals to x. Image along y equals to x. It looks as if you are taking the image of the function, but you understand what's happening. You start off with a function xy, you get yx as the output. Okay, so that's what's happening. So verify if this particular function is a linear operator or not. That is your job. Right? Why don't you guys verify if this is a linear operator? So in this case, what will help is you can take the two vectors as, or instead of xy, what you can say is f of x1 comma x2 is equals to x2 comma x1. So that will make job easier. The first input you take is x1 x2. The second input you take is y1 y2. So that will make checking property number 1 easy. Otherwise you'll get confused. By the way, when we write x and y, these are all vectors. Goes without saying in linear operations, these are all vectors. Is first property satisfied?
No, sir.
No? Okay, so let us see. F of x1, x2 plus y1, y2.
It is.
What is the sum of these vectors? Dhruv, what is the sum of these vectors?
Sir, it is x2 comma x1.
No, the
plus
sum of these vectors. How do you add vectors?
x1 plus y1
Yeah.
comma x2
x1
plus y2.
x2 plus y2. Okay. So what will be the output of this vector?
y1 plus x1 comma y2 plus x2.
No. No. Anybody else? What will be the output of this thing?
Sorry, y2 plus x2 comma y1 plus x2.
Very good. Okay. y2 plus x2 is basically the same thing as x2 plus y2. Now, f of x1 comma y1, sorry, x1 comma x2 plus f of y1 comma y2. What will this be?
x2 comma x1 plus y2 comma y1.
Which is what? It's the same thing, right?
Yes.
So it satisfies property number 1. So that's how you check it. So it's very simple. If you have to check if something is a linear operator or not, you have to check these two properties, and it's very straightforward. So they don't give very
This
complicated
is only one
things.
property, no? The other one.
Yeah, the other one also you'll check. I'm leaving it into you guys, but yeah, you'll find that it's very straightforward. Okay. I mean, if you multiply these vectors by 2, the output will also get multiplied by 2.
Yes.
So it's as simple as that. So, so that's not very complicated. So second property will also pass through. So this is a linear operator. Okay, so this is the linear operator. See, other examples which I'm leaving up for you guys is this thing, x comma y gives y comma minus x. Now this is a very, very popular linear operator. This is rotation by 90-degree counterclockwise. So what is 90-degree counterclockwise rotation? So suppose you start off with some vector v, which looks like this. Let's say this is your vector v. Now you rotate it 90 degrees. So what you get is this vector. Yeah. You'll get this vector v perpendicular. I call it v perpendicular. Right? So using all types of trigonometry, you can always find what this vector is going to be. So suppose you know what this vector is in x and y. So suppose you know this x1 and y1. So you know theta, this is going to be theta. So you know this is going to be theta and so on. The length is going to be same for both of them. So this value, this length will be equal to this length. So this point is going to be x1 now, right? And similarly, this length will be equal to this length. So this point is going to be minus of y1 now. This point is x1. This point is minus y1. So the vector which was initially x1 comma y1 now becomes minus of y1 comma x1. Its x coordinate becomes minus y1. Its y coordinate becomes x1. So x1 y1 transforms into minus y1 comma x1. So this is your 90-degree counterclockwise rotation function. For any x and y, this is going to be your 90-degree counterclockwise rotation function. And this ninth one is just projection onto the x-axis. What is projection onto the x-axis? So suppose you have some vector x comma y, which looks like this, x comma y. The projection is just its x coordinate, x, the x coordinate of this function. If it is minus x comma y, if it is, let's say, minus 2 comma 3, the output is just going to be minus 2. So whatever the x coordinate, only the x coordinate comes out as the output. Now these three are important class of linear operators because they relate vectors with matrices in a very nice, beautiful way. Now, this is something which is used a lot. If you think of your devices, if you think of your device, let's say, if you think of your phone, when you go from portrait mode to landscape mode, what happens is that the pixels, they appear in the pixels. You can think of your pixels as a matrix, right? The pixels are basically a matrix. And when you rotate them, the same phone with the same arrangement of pixels is now showing that image in a 90-degree manner. So what's happening is that the vector of pixels is rotated by 90 degrees. Right. So this is something which has applications in real life, in a lot of real things that we do a lot of times. We don't realize it, but these are simple lines of code and they are all very simple because of the fact that linear operators exist. And it's not very complicated to go from landscape to portrait and so on. Or even though, no matter what, how complicated your phone device is, okay, the more pixels you have on your screen, the more complicated that matrix is going to be. A simple 480p screen will have just 480 cross something pixels, but today we are saying 4K screens. So 4K screens are having 4 times the pixel of a 1080p, say double, twice the length, twice the breadth. So It is very complicated, but because linear operators are so easy to work with, they make math so easy that these things happen in a fraction of time. It doesn't take a lot of processing power to go from landscape mode to portrait mode and so on. So in 7th, 8th, and 9th, we are going to find this F matrix which does this job. So there's some matrix F which when multiplied to a vector like x comma y will give the output as y comma minus x. So that will be this particular. So we are going to look at what these matrices are doing and how do we find them. 10th is basically something which is not a linear operator. This is the distance function x square plus y square. So you can check the two properties, it won't be satisfied. So the next part is, the important part is how to find the vector of a linear operator. So in first section, we just identified when is a function a linear operator or not. Now that I have established that yes, something is a linear operator, like we saw here, 7th, 8th, and 9th, these are linear operators. So what is the matrix which can get this function represented? Okay. All right. So getting this function, to get this function, let's start the story here. So there's some function, there's some matrix A. Let's say there's a matrix A, which basically gives me the result that A times X is equals to Y for all X belonging to V and Y belonging to W, where the function F is defined from V to W. So my aim is to find this matrix A. I have to find this matrix A. So how do I find this matrix A? So suppose this vector V, suppose the basis vectors in vector E are E1, E2, and so on till En. These are the basis vectors. For example, let's say V is equals to R square, then the basis vectors are going to be 0, 1 and 1, 0, or 1, 0 and 0, 1. Okay, so these are the basis vectors. You can represent all vectors in R square as a linear combination of these two vectors. So these are the basis vectors. Okay, and let's say W is a vector in again R square. Then its basis vectors are also going to be F1, which is 1, 0, and F2, which is 0, 1. I should write 1, 0, and 0. That is the norm. Doesn't make much of a difference, but yeah, that's the norm. So let's say these are different vector spaces. Sometimes they might be the same vector space. So I don't care about that. The point is that X, any vector X here, it can be represented as a linear combination of its basis vectors. It's going to be some x1 times e1 plus x2 times e2. Right. So A times X, because it's a linear operator, because it's a matrix multiplication, will just be A times of x1 e1 plus x2 e2, which is just x1 times A of e1 plus x2 times A of e2. So if I were to know this AE1 and AE2, then my job becomes easier. I just need to get what is x1 and x2, and my job would be done. Right. So that's what I need. I need to find what's going to be A times E1 and what's going to be A times E2. Okay. Now, this final thing is going to be y. Now, what is y? Y is a representation of its basis vectors. Y is y1 f1 plus y2 f2. Right. So this y1 f1 plus y2 so this equation is going to be the holy grail in order to solve for A. Remember, what am I looking for here is A. I'm finding what is A. I'm looking for A. A is the unknown here. So I'm going to use such equations in order to find what's going to be my A value. Okay. So A times E1. So let's say my A times E1 is A11 F1 plus A21 F2 and so on. And similarly, I can represent all these things. So the crucial building blocks are these A times E1s, AEI. AEIs are crucial things because if I know what's happening to the basis vectors under the linear transformation, all vectors are just linear combinations of basis vectors. So if I just figure out what's happening to the basis vectors, I can find out what's going to happen to the eventual vector. So let's look at this 90-degree counterclockwise rotation matrix. So let us look at the example of 90-degree counterclockwise rotation. Okay. So I told you that E1 is equals to 1, 0, which in R square is going to be represented by this particular vector, 1, 0. What vector do I get when I rotate this vector by 90 degrees counterclockwise?
0, -1.
Is when I rotate it 90 degree counterclockwise like this, what vector will I get? What is this vector?
0, 1.
0, 1. So this is my A of E1, 0, 1. Okay. Now E2 is 1, 0. The second basis vector is 1, 0, 1. What happens when I rotate this vector by 90 degree counterclockwise? You can give the answer before I draw it.
0, -1. -1, 0, sorry.
-1, 0. Good. So A of E2 is going to be -1, 0. Because if this is my vector 0, 1, 0, 1 looks like this. If you rotate it 90 degree counterclockwise, you're going to get this vector. So that is -1, 1. Okay. So first I need to find out what is this AE1 and AE2 in F1 and F2 terms. Right. So 0, 1 is, let's say, some y1 times 1, 0, which is basically my F1, plus y2 times 0, 1, which is basically my F. Okay, now 1, 0, 0, 1, I'm not looking at them as E1 and E2, I'm looking them as F1 and F2. So what is going to be the values of this y1 and y2 now? What y1 and y2 will solve this equation?
0 and 1.
Very good. Y1 equals to 0 and y2 equals to 1 will solve this equation. Because this thing is basically same as this. So that solves A E1. So A times E1 is equals to 0 times F1 plus 1 times F2. So that's equation number 1. What about A times E2?
So 1F1 plus 0F2.
Think about it. This is A times E2. I want them in terms of this and this. So write it down in your notebook and give me the answer again.
Sir, minus 1, comma 0.
Very good. Okay. So minus 1, 0 is equals to, let's say, Z1 times 1, 0 plus Z2 times 0, 1. So obviously there's a minus here. This is plus. So this Z1 has to be minus 1. This Z2 has to be 0. So minus 1 times F1 plus 0 times F2. Okay. So once you arrive at this point, the next step is A times X is basically A times of X1 E1 plus X2 E2, which is X1 times A E1 plus X2 times A E2. Now A E1 is 0 F1 plus 1 F2. X1 times 0 F1 plus 1 F2 plus X2 times minus 1 F1 plus 0 F1. Okay. So this is just going to be equal to X1 times F2 minus X2 times F1. Okay, so this is one way to do it without matrix multiplication. So if you just want it in terms of X1, X2, F1, F2, you can do this entire thing without getting the matrix. I'll tell you how to get the matrix as well. But this is one way to do it. If you want to avoid all the matrices, if you just want to find it in terms of vectors, this is how you can do it. X1 times F2. You know the values of F2 and F1. We have already established them. F1 and F2 are these two functions. That's why these two vectors. So you just substitute those values and you'll get your thing. Okay. Now, this is just X1 times F2 is 0, 1 minus X2 times 1, 0. Right? Now this minus X2 times 1, 0, I want to you instead write it as plus X2 times of minus 1, 0. So it's the same thing. Okay, I took that minus and multiplied it with the matrix. So when I multiply the entire matrix with the negative, all numbers go negative. So 1 became minus 1, 0 became minus 0, but minus 0 is same as 0. So this is X1 times 0, 1 plus X2 times minus 1, 0. So X1, X2. So if I want to write this as a matrix multiplication, so this becomes a row by column type of a matrix multiplication. So what's it going to be? 0, 1, minus 1, 0. Uh, 0, 1, row 1, column 1. Yeah. X times X1 times 0, 1, minus 1, 0. So this is going to be your Y1. So this is the matrix A, which multiplied from the right with any vector x1, x2 will generate this y1. Okay. I wanted to find a matrix. Okay, so it's not important where you find the matrix from the left hand side or the right hand side. Once you find this matrix, you can use any x1, x2, multiply this matrix from the right, and you will get this final output. If you want to find the left matrix, obviously it's going to be something different. And maybe you'll have to figure it out from here which matrix you can use. Getting the right matrix is generally easier. Like once you reach this particular setup, you can get the right matrix pretty easily. The right multiplication matrix. So you take any x1, x2, you multiply it like this. What you will get is the final output y1, y2. So let us look at an example. So I told you that if I rotate a vector, let's say I take a vector 2, 1, and I rotate it by 90 degrees, what I'll get is the vector 1, minus 2. 1, minus 2, right? No, minus 1, 2. Yeah, minus 1, 2. So this is the vector I get. So let us put 2, 1 here into 0, minus 1, 1, 0. So what is this going to be? Okay, so if you do matrix multiplication here, so this is just going to be, oh no, I found the left matrix itself, right? Move on into column. Oh no, this has to be the left. Sorry. I got confused with dimensions. So this is 2 cross 1. So this has to be 2 cross 2. So 0, 1 and minus 1, 0. 0, 1, minus 1, 0. Should this be the one? Row 1 into column 1.
Yeah,
It's
it's
equals to minus of x2, and 1, 0 is x1. Yeah. Minus x2, x1. So that's going to be minus 1, 2. Sorry, I got confused with the dimensions. Yeah, it is the left matrix. So that's how you do it once you find these x1, x2, 0, 1, minus 1, 0. So all you need to do is just figure out what happens to the basis vectors in E1 and E2. How do they go in F1, F2? So once you figure that out, then the entire thing is pretty straightforward. So let's do one more example so that we can thoroughly concrete our steps methodology. So this is basically the same thing given in a shortcut format. So if you have A1, A2, and so on in these terms, A11, A21, AM1, and so on, so you can just write them in this manner. So if these vectors are A11, A21, AM1, so the first row of coefficients becomes the first column of coefficients. The second row of coefficients, A12, A22, AM2, becomes the second column of coefficients. So the rows which you see in coefficients, they start becoming as columns. Okay, so let's apply this technique to the seventh part, f of x, y is equals to y, comma, x. So again, a times some x vector is equals to some y vector, where ax comes from R square space with the basis vectors 1, 0, and 0, 1. Y comes from, again, R square space with the same basis vectors 1, 0, and 0, 1. But this for simplicity, I'm going to call E1, E2, and these I'm going to call F1 and F2. So this is the mirror image function. This is the mirror image function. So let us look at what happens to the basis vectors. So I'm taking mirror image along this y equals to x line. So what is the mirror image of 1, 0 along this mirror? What is going to be the mirror image? Suppose you are standing here, where will your image form? I know you have done mirror images, plane mirror, convex, concave mirrors, and lenses, because we did it in 9th standard in physics. But very simply, if you place an object at 1, 0, where will its image form if the mirror is kept here?
So
0, 1.
Very good, 0, 1. Okay. So a times E1 is equals to a times 1, 0 becomes equal to 0, 1, which becomes 0 times F1 plus 1 times F2. All right. So the coefficients of importance are 0 and 1. Now, if E2 is the object, if you place an object at 0, 1, where will its image form? Where will the image form if this is the mirror? Suppose it's a two-way mirror. Two-way mirror है, दोनों साइड दिखता है. बाहर वाले को खुद की, इधर वाले को खुद की तस्वीर दिखती है, इधर वाले को खुद की तस्वीर दिखती है. So where will this guy's image be placed if the mirror is here?
So 1, 0.
1, 0, perfect. 1 times F1 plus 0 times. So the coefficients are 1 and 0. So all you need to do now is make this thing as your row 1 and this other thing as, sorry, column 1, and this other thing as column 2. So this is your matrix of transformation. 0, 1, 1, 0. So let us look at if this works or not. 0, 1, 1, 0 times x, y will be what? Yx. And that's what I wanted. That was the function that I was looking at. F of xy should be f of x comma y should be equal to y comma x. So this is what I wanted. So I take input as xy, I get yx as the output. Remember, okay, so this technique makes your job pretty easy. I've explained you the details, but this technique is very easy. You just write down what your E1, E2s are, write down what your F1, F2s are, and just this row will give you your first column. This row will give you the second column. Okay? So let us look at a little complicated problem.
So can you once just revise this method? Like
I'll revise it, but with a complicated one.
Okay.
I'll revise it, but with a complicated example now. A 2-degree polynomial. Card differentiation. The differentiation of a 2-degree polynomial. So I'm making a claim that the differentiation of a 2-degree polynomial is a linear transformation. The first time I heard this, I was like, what? Differentiation? How can differentiation be a linear transformation? For us, differentiation is not even a function. We don't even treat differentiation as a function. Here we are saying it's not just a function, it's a particular type of function known as linear transformation. For us, linear differentiation is a methodology. But if you really think about it, if you really think about it, why is differentiation a function? So suppose my domain A is the class of all 2-degree polynomials. What are 2-degree polynomials? 2-degree polynomials are of the format ax square plus bx plus c. So the power, the highest power of x decides what is the degree of the polynomial. So this is 2-degree. 1-degree polynomial is of the format ax plus b. 3-degree polynomial are of the format ax cube plus bx square plus cx plus d, and so on. Okay. So the highest power which is accorded to x becomes the degree of polynomial. In particular, these are single variable polynomials, only x. When you have x and y, then 2-degree polynomials in x and y will look like ax square plus bx plus cy square plus dx dy plus exy plus f. So this is going to be 2-degree polynomial in x and y. So all combinations of x and y where total power must be less than equals to 1, less than equals to 1. So that's 2-degree polynomial, 2-degree polynomial in x and y. But if you really think about it, coming back, why is this differentiation a linear transformation? If A is the set of all 2-degree polynomials and B is again the set of all 2-degree polynomials, then what happens in differentiation is you start from a 2-degree polynomial and you end with a 2-degree polynomial. What is going to be the differentiation of ax square plus bx plus c? What will be the differentiation of this guy?
2ax plus b.
2ax plus b, which is basically a 2-degree polynomial. It's technically a 1-degree polynomial, but for a equals to 0, if a becomes equals to 0, 2-degree polynomials actually subsume 1-degree polynomials. So you can take the domain as 1-degree polynomials, or you can take it as 2-degree polynomials. I don't care. But for simplicity, I'm going to keep it as 2-degree polynomials because that makes this question easier to operate.
Sir, I didn't get how is it a 2-degree polynomial? 2x plus b.
2ax plus b?
Yes.
Because you can write it as 0 times x square plus 2ax plus b.
Okay, so as long as it, so that way we can make any like
Yeah, so
equation
that's what
of
I'm saying. So this is your 0-degree polynomial, which is basically all constants. This is 1-degree polynomial. This is the set of 2-degree polynomials. This is the set of 3-degree polynomial. This is the set of 4-degree polynomials, and so on. Okay, so they are subsets, sorry, supersets of each other.
Okay.
All right. So you know, I mean, when I define the function x square, I can define it from R to R, or I can define it from R to R plus. It doesn't make a difference. Technically, I should be using R plus because x square will only take positive values. But I usually write it as R to R. I don't care about it. Why? Simplicity. I don't want to find unnecessarily complicate things. So I'm saying use the same 2-degree polynomial as domain and codomain, because even though you are not strictly using all 2-degree polynomials, you are strictly only using 1-degree polynomial, still your basis vectors will remain the same. So that's going to be the simpling thing here. That when I use the same domain and codomain, my E1, E2, E3 and F1, F2, F3 will remain same. So I don't have to worry about it. So that's the idea. But frankly, you can try it with 1-degree polynomial as your codomain. I don't care. Maybe you'll learn something. I have never tried it. Maybe you'll get a different matrix. Okay, so since we are saying it, why not try it as a homework? Okay, try doing it and remind me to discuss it in next class. So we'll take it up and we'll discuss what happens. So coming back, I want to find this 2-degree polynomial. So first of all, I want to find the basis vectors in 2-degree polynomial. So let's say the basis vectors are, so a 2-degree polynomial is basically ax square plus bx plus So the bases are basically x square, x, and 1. So if you think about your x, y, and z axis, okay, so if you think about your x, y, and z axis as the axis of x square, axis of x, axis of 1, then every element in R cube represents a 3-degree polynomial. So you suppose you take this point, which is 1, 2, 7 in R cube. Then this is just 1 times x square plus 2 times x plus 7 times of 1. So this is x square plus 2x plus 7, which is a 2-degree polynomial. So what I'm saying is that a 2-degree polynomial, if you consider x square as the x-axis, x as the y-axis, and 1 as the z-axis, then a 2-degree polynomial is nothing but some point in the R3 space. It is some point in the R3 space. So I can take the same vectors as the basis here. So you can take in my vector space B, which is basically my 2-degree polynomials. I can take E1 to be equal to 1, 0, 0, E2 to be equal to 0, 1, 0, and E3 to be equal to 0, 0, 1. So 2-degree polynomials. So stop thinking of 2-degree polynomials as 2-degree polynomials and start imagining them as some points in R3 where every point represents a different 2-degree polynomial. Okay. Every point in R3 is basically a 2-degree polynomial. So the basis vectors are going to be 1, 0, 0, 0, 1, 0, and 0, 0. Now I'm saying that it maps in again 2-degree polynomials. So these are also going to be equal to my F1, F2, F3. Because my W space is also my 2-degree polynomials. Okay. So now A of E1. A of E1 is basically when I differentiate 1, 0, 0. Now 1, 0, 0 here is this point. This is basically just x squared. So this is d by dx of x square, which is 2x, which is this point. Zero to 0. Which if I want to represent as F1, F2, F3, so this is going to be 0 times F1 plus 2 times F2 plus 0 times F2. Right? So suppose I want to differentiate A of E2, which is basically E2 is 0, 1, 0. So 0, 1, 0 is basically x. So d by dx of x would be what? What would be differentiation of x? 1. Now, if you want to represent 1 in this R3 space, what point would it be? In R3 space, where x square, x, and 1 are the axis, what point will be the
0, 0, 1.
0, 0, 1. Perfect. 0, 0, 1. So 1 is basically 0, 0, 1, which I want to represent in this format. So 0 times F1 plus 0 times F2 plus 1 times of F3. Now finally coming to A of E3. So d by dx of 1. What is differentiation of constant
0.
1? 0. Which will be 0, 0, 0. Which will be 0 times f1 plus 0 times f2 plus 0 times f2. Now the final step is finding the matrix. So finding matrix is very easy. I gave you the shortcut. The first row 0 to 0 becomes the first column 0 to 0. The second row 0, 0, 1 becomes the second column 0, 0, 1. And the third row 0, 0, 0 in that order becomes the third column 0, 0, 0. Now you multiply this with any vector. Let's say I want to find the differentiation of ax square plus bx plus c, the general 2-degree polynomial. So you told me that ax square plus bx plus c ka differentiation is 2ax plus b, which if this is in vector format ABC, this in vector format should be 0 times 2a times b. So I should be getting this as the output. So am I getting this as the output here or not? Row 1 times column 1, 0. Row 2 times column 2, 2a. Row 3 times column 3, 0 to ab. So differentiation is nothing but a linear transformation, which is basically a matrix multiplication for polynomials, by the way, only for polynomials. This works for polynomials. Doesn't work for sine theta, cos theta. It doesn't work for exponential functions. Works for polynomials. So you have to start imagining x, y, z as x square, x and y. Now what you're saying is that if you want to consider only, let's say, 1-degree polynomial as the codomain, so that is a homework. So in that case, 2ax plus b in 1-degree polynomial will become the vector 2ab. So instead of 2ab here, I would have just 2a and b. So corresponding to that, you have to find this matrix B, which gives a times this equals to 2a into b. Okay, so that is one homework. The other homework is this 9th one I have not done. So this is done. Okay, so everything that I have done is when v and w are same. What I have given to you is when v and w are different. Okay, so because I'm leaving something for you guys to be new. Okay, so I've done it in a set pattern where even EIs and FIs are same. I'm giving you something to think about where EIs and FIs are different. All right. So this is a more complicated sort of a thing. This is, you can forget this example. So in this case, what we do is 120-degree counterclockwise rotation when looking at the origin from first octant. Okay, so the first octant is basically x equals to y equals to z line. So you're looking at x equal through, your eyes are along the x equals to y equals to z line. So this is where your eyes are. So you look at this vector and you rotate it by 120 degrees. So this is complicated, three-dimensional rotation and all those things. Forget this. Out of question. Okay, the next thing is change of basis. Now, change of basis is a very interesting concept. So I told you that there are multiple bases in there are multiple bases in R square or any vector space. So suppose this is your home. Now you're living in, you are living at your home H, which is basically the origin, and your friend lives here, which is at a vector, let's say 3, 2 kilometers. Okay. So he's living at 3.2, 3, 2 kilometers. So you tell him that from your house, you go straight for 3 kilometers, take a left and come straight for 2 kilometers, you'll reach my house. 3 kilometers, left turn, 2 kilometers. But your friend, let's say he happens to be from United States. He doesn't understand kilometers. Okay? So you can't work with kilometers. So right now you're using kilometers. He says, I don't understand kilometers. Tell me miles. Obviously, to divide by miles, you divide it by 1 by 4.6, but that will spoil my entire example. So let's say you want to find the basis in terms of miles. So what you have done is, for him, you have said that you live at 3, 2. So this is basically 3 times 1, 0 plus 2 times 0, where your units are kilometers. I want to use the units as miles. So I want to use it in terms of miles. Now 1 kilometer, basically 1.6 miles are 1 kilometer. So what is 1, 0 will become 1 by 1.6, 0 and 0, 1 by 1.6. So I want to represent this vector, this particular point, your friend's house, in terms of these bases. I have the location in terms of these bases. I want to find it in terms of these bases. To give you another example, suppose your E1 and E2 are, let's say, 1, 0 and 0, the standard basis. We call this as the standard basis. Now, I want to represent the same vector 3, 2 in terms of some F1, which is, let's say, 2, 0, and F2, which is, let's say, 0, 1. Or let's say 1. Or let's say 1. 2, 0 and 1, 2. 2, 0 and 1, 2 are also bases. They are independent of each other. So any two vectors which are linearly independent will be a basis in R3. So if you talk about a general Rn vector space, any n linearly independent vectors will form a basis. Any n linearly independent vectors will form a basis. So that's the rule. You take any n independent vectors, they will be making a basis. So now, instead of 1, 0, I want to use these terms. Now, obviously 3, 2, I know 3, 2 or 3, 2 is basically 1 times 2, 0 plus 1 times 1. Right? But I don't want to do it like this. I want to find the matrix which does this linear transformation. So change of basis is basically a linear transformation. So I want to find that matrix A. So it's very straightforward what I'm going to do. Yeah. So first I want to represent 1, 0 and 0, 1 in terms of F1 and F2. So this is what I want to do. Yeah. So this is what I used to do initially. If you remember, the first step was always find A of E1 and A of E2 and represent them in terms of F1 and F2. But right now that becomes a little tricky. Why it becomes tricky is, so suppose I want to find A of E1. Okay, and So I want to find this in terms of F1, F2, some A1 times F1 plus some A2 times F2. Okay, so A of E1 is 1, 0. 1, 0 is some A1 times of, let's say, yeah, so this was what? 2, 0 and 1, 2. Now this can still be easy, but if you look at E2, E2 is 0, 1. 0, 1 as a linear combination of these two vectors could be tricky to find A1 and A2. So obviously this method becomes complicated because representing E in terms of F is complicated. Representing F in terms of E is relatively easy because E is the standard basis. F1, if I want to represent F1 and F2 in terms of E1, E2, that is very straightforward. So F1, which is basically 2, 0, is 2 times E1 plus 0 times E2. And F2, which is basically 1, 2, is 1 times E1 plus 2 times E2. So you see, I don't want to use the direct way going from E to F. I want to use the reverse way, which is coming from F to, because the reverse thing is easier to figure out, right? Because even doing this bit is a little complicated. So I don't want complicated steps. The problem itself is pretty complicated to begin with. And then I complicate it further by taking complicated steps. It's not going to be easy. So what I say is that let's say E1 is some linear combination of these F vectors. E2 is also some linear combination, which I don't know what the combination is. I don't try to find out what that combination is. Okay. So I just say that, let's say E1 is equals to some linear combination of these vectors, some C1, A11 times F1. Yeah. C1 equals to A11 times F1 plus A21 times F2, and C2, no, E1 and E2. E2 is equals to A21 times F1 plus A22 times F2. Then I know that my linear transformation matrix A will be equal to, these two numbers will go as the first column. So that's going to be A11, A21. And these two numbers will become the second column, A21, A2. Right? So this will be my matrix in such a way that A times X will give me equal to Y. Obviously, these A's are unknown right now. These A's are unknown right now. But what I can do is I can multiply both sides with A inverse. So what I get is X is equals to A inverse times of Y. And I can generate this A inverse pretty easily. How can I generate this A inverse? So reverse the problem on its head. So let's say F1 is equals to B11 times E1 plus B21 times E2. And F2 is equals to B12 times E1 plus B22 times. And then the matrix B11, B21, B12, B21, B22 will be your A inverse. And since it's an invertible matrix, it will be an invertible matrix. You can take the inverse of A inverse to find this. So what I'm saying is calculating this is complicated because representing the basis vector in terms of some other basis is difficult. But finding the A inverse is easy. So we want to find A. By the way, we don't want A inverse. We want to find A. But finding A is complicated. So what we do is we find A inverse and then we invert it to get it. All right. So let's get back to our original example where we had E1 equals to 1, 0, E2 equals to 0, 1, F1 was 2, 0, and F2 was 1. Right. So these were my vectors. So let's deploy our method. So 2, 0 equals to B11 times 1, 0 plus B21 times 0, 1. So what's going to be B11 and what's going to be B21?
2, 0.
Very good, 2, 0. So I'll write that as the first column. The second equation F2, so 1, 2 is equals to B12 times 1, 0 plus B22 times 0, 1. So what's going to be B12? 1, 2. Very good. So this thing is nothing but writing the same vectors 2, 0, 1, 2. You don't even have to do this. Okay, when you're changing the basis, you don't even have to do this entire step. I just showed this entire step, but in reality, you don't even need to do. Just write F1 here and F2 here, and that's true for any Rn space. You can take R4, R5, R6, R10, any Rn space, it's going to be this. So this is my...
So because that E1 and E2 is a basis for F1 and F2.
Exactly, because E1, E2 are standard basis. Because E1, E2 are standard basis, that's why this works. Okay. Now this is your A inverse. So after this, we just find the A vector. So A vector is the inverse of this thing. So A vector is the inverse of this particular matrix. So what's going to be the inverse of this matrix?
2 minus 1, 0, 2.
Is it that simple? Have you found it?
So we can just, when it's 2 by 2, we just have to exchange the first and fourth columns and negative signs on the second and third
Okay.
element.
2, what do you think? 2
minus
1?
0 and 2.
0 and 2. I think we'll need to divide it by something as well because the determinant cannot be same. See, determinant of A and determinant of A inverse should be reciprocals of each other. So what you're saying is true, but then I need to divide this by determinant of A square. What you're saying is true, but I'll need to divide it by determinant A. Yeah. Because otherwise what will happen is that yeah, I need to divide it because otherwise this determinant is 4. And if you just look at this upper matrix, its determinant is also 4. So if I take determinant of A into A inverse, it will be determinant A into determinant of A inverse. So that will be 4 into 4. So that becomes 16. But that cannot be true because A into A inverse is basically identity matrix and its determinant should have been 1. So I'll just need to divide it by determinant of A couples here. So that will make my thing easier. What you're saying is correct. It's coming from that cofactor thing that we are doing. That the cofactors, you can use cofactors formula to get the inverse. Once you find the inverse, then you can easily get this A inverse matrix. The point is, yes, you get A inverse, you take its inverse to get A inverse ka inverse, which is basically A. And this will be A. Now, once you find A, after that, the job is pretty easy. You Just write down any matrix. So suppose I wanted to do this, take this 3, 2 and represent it. So take this A matrix times 3, 2. You will get the combination in the other bases. Okay. So if you're correct, let's use this technique. Let's see if you're correct. If not, then I'll have to find that inverse actually. And then divide it by 16. I'm going to divide it by 16. Right. Yeah. Should I divide it by 16? Let's see. Row 1, column 1. So 3 2s are 6. 2 minus 6 minus 2 is 4. And 0, 2. So that is 3 and 2. So that is 4. 4, 4. That's not what I was looking at. I think there's some problem with A inverse. Let's find A inverse. Let's find A inverse. Inverse of 2 cross 2 matrix. Done. That was the matrix 2102. 2102. Okay, half minus 1 by 4, 0 half. So that is it. So half minus 1 by 4, 0 half. Half minus 1 by 4, 0 and half. So that's my A matrix. So let's multiply this matrix. Half minus 1 by 4, 0 and half. Yeah. So I have basically divided everything by determinant of A, all the elements by determinant of A, and then put a negative sign there. So this would be equal to, okay, what you're saying was correct actually. 4, 4 divided by 16. Chalo, let's do it. Half times 3 minus, so 3 by 2 minus half, and this becomes 0 plus 1. So that is 1, 1. So this is what I wanted actually. Right? So once you find your A, you get your answer pretty straightforward. So all you need to do is, so in a nutshell, what you need to do is, suppose you have basis vectors E1, E2, and En, and you have some vectors F1, F2, and Fn. Just write down these vectors in matrix format, F1, F2 till Fn. Take the inverse of this. And let me call this matrix as A. Then A times whatever vector you have, X vector, will be the X prime vector that you want in the new basis. This is in the standard basis. So that's pretty straightforward. So this is the mathematical proof of what we have done here. So you can go through it. I don't find it very necessary. So if you want, you can go through it. Okay. All right. conjugate matrices, two n cross n matrices A and B are called conjugate if there exists a non-degenerate matrix C such that B is equals to C times A times C inverse. So if you can represent B and A in this format, then they are called conjugate matrices. You don't need to know this definition. If it is used in some problem, then first the exam will define this definition and then they will ask you a problem-based one. So I don't think remembering conjugate matrices is that important. The reason they have given here is because if let's say A is a linear operator going from B to B with matrix A in the old base and with matrix A prime in the new base. Okay, so if you are doing some linear transformation A B to B, okay, so suppose I know the 90-degree rotation in my standard basis. I've done the 90-degree rotation in my standard basis. Okay, the 90-degree rotation matrix, if you all remember, or the mirror image. Let's do mirror image. Mirror image was easy. The mirror image matrix was 0, 1, 1, 0. Right? This was my mirror image matrix A. Now, suppose I don't want to do it in the standard basis. I want to do it in this basis using this matrix. So suppose matrix B, suppose I call this as matrix B, half minus 1 by 4, 0, half, half minus 1 by 4, 0 and half. So suppose I want to do the find the transformation in this particular basis. So what I can do is suppose I have some vector in the in the new basis, right? So first I'll bring it in the current basis using B. B times X prime gives me the vector in the original basis. Then what I'll do is I'll do A, which gives me the mirror image, and then I'll do B inverse. So this is just going to be B inverse times A times B of X prime. So this will give me the mirror image in the new basis. So B inverse A into B is the linear transformation of mirror image for the new basis. So if I have the linear transformation in the standard basis, and if I have the matrix of conversion to standard basis, from standard basis or whatever, then I can use B inverse AB to get the linear transformation in any other basis. All right. Eigenvectors, eigenvalues. So this is an important thing. So according to me, in this chapter, two things are important. One is identifying when something is a linear transformation. Finding the matrix of linear transformation, I don't think it's very important because as we saw, it's pretty complicated. But identifying if something is a linear transformation or not is important. And the second thing which is important is eigenvalues and eigenvalues. So what are eigenvalues, eigenvectors? It's very easy. Let A be a n cross n matrix. The non-zero vector x is called the eigenvector of A with eigenvalue lambda if A times x is equals to lambda times x. So A is a matrix. By the way, A is a matrix. Lambda is a scalar. X is a vector. So remember these things. I told you these things again and again. All capital letters are matrices. Okay, all capital letters A, B, C, these are all matrices. All small letters X, Y, Z, these are all vectors. All Greek letters alpha, beta, gamma, delta, these are all scalars. So that is the convention. It is followed throughout. It is followed across all books, all exams, that whenever you see capital letters, it's going to be a matrix. So 8x is lambda times of x. So what your meaning is that when you multiply this matrix A with any non-zero vector x, it will be basically like multiplying the vector x with some constant value lambda. Okay. So then lambda becomes the eigenvalue and x is called the eigenvector. So how do we find this eigenvalue? So the number lambda is an eigenvalue of matrix A if and only if determinant of A minus lambda E is equals to 0. So what we are saying is Ax is equals to lambda x. Right? So what we are saying is Ax is equals to lambda x. Right? Ax is equals to lambda into x. Okay. Now lambda x is basically lambda into identity matrix into x. Okay, lambda is like a scalar, like 2, 3 or something like that. Identity matrix is this thing and this thing is this thing. So Ix becomes a n cross n matrix. So what we are saying is, so this A is, let's say, n cross n. X is, let's say, n cross 1. Lambda is 1 cross 1 because it's a scalar. Identity matrix again n cross n. Not 1 cross 1, it's basically a scalar. So it's not a matrix. And this x is again n cross 1. So the reason I'm imposing this I in between is to convert this Ix into a n cross 1 matrix. So this becomes lambda times Ix, where Ix is a n cross n matrix. So now, what I want is lambda I into x. Sorry. Lambda I into x. Lambda I is a n cross n matrix, and this x is a n cross matrix. So what I have is finally Ax is equals to lambda I into x. So x can be taken common. So this becomes Ax minus lambda I into x is equals to 0. So this becomes A minus lambda I into x is equals to 0. When I say 0, it is basically 0. And then I take determinants on both sides. So A times lambda I must be, so this just means that determinant of A times lambda I, this just means that determinant of A minus lambda I must be equal. So determinant of A minus lambda I must be equal to 0. So this is the proof of that. Now, yeah, because x is a non-zero vector, by the way. X is a non-zero. X is a non-zero vector. So Ax is equals to 0. Okay, Ax equals to 0 means what? Suppose instead of A, I write Bx equals to 0. B matrix into X vector equals to 0. Means what? Either X vector, X is a 0 vector, or B is something jiska X is something in the null space of B. So either X vector is 0 or X belongs to null space of B. Right? Bx equals to 0 can have only two options to be solved. Either X vector must be 0 or X should be a vector in the null space of B. So if X is a vector in null space of B, then it automatically means that B cannot be a full rank thing. This implies that B is not linearly independent columns. The columns of B cannot be linearly independent, which implies that determinant of B must be equal to 0. If columns are not linearly independent, then determinant is 0. Remember, B in our case, in this case, is an n cross n matrix. It's a square matrix. So a square matrix satisfying Bx equals to 0 when x is non-zero has only one option, that its rank is less than n, which means that its columns are not linearly independent. which means that its determinant has to be 0. So if determinant of B equals to 0, remember B is just A minus lambda I. So determinant of A minus lambda I must be equal to 0. So after this, all I need is to find the value of lambda. So just take the determinant of A minus lambda I and put it equal to 0. So that will give you the eigenvalues for values of lambda. Remember, what am I looking for here? Lambda. I'm searching for lambda. A will be given to me. I'm searching for lambda. So let's do a quick example. Find the eigenvectors and eigenvalues for this matrix. 3, 4, 5, 2. So 3, 4, 5, 2 minus lambda times I. So that is just going to be lambda times 1, 0, 0, 1. So that is 3 minus lambda, 2 minus lambda here, 4 and 5 here. So the determinant of this thing must be equal to 0. So I give you any matrix like A, B, C, D, and I tell you find the eigenvectors lambda of this. So you just straight away go to A minus lambda, B, C, D minus lambda, and take this determinant equals to 0. So you'll get a quadratic in lambda, like here. You get a quadratic, you solve the quadratic, you get the eigenvectors. So lambda vector values here are going to be -2 and 7. Now, once you find the lambda values, after that, we are going to find the x1 and x2. So you substitute the first lambda value, that is, okay, let's substitute lambda value 7. So A minus lambda I. So A minus lambda 2 times of identity matrix, which here is represented as E instead of I. So A minus lambda I, A matrix is given to you as 3, 4, 5, 2. 3, 4, 5, 2 minus 7, 0, 0, 7. So that will give you this matrix. So A minus lambda I times X must be equals to 0. So eigenvector is basically the solution to this null space thing. So now I have A minus lambda I, which was my B vector. I want to find for which X does this Bx become 0. So you just find that vector in the null space. So you just do this matrix multiplication, B times x1, x2 is 0, 0. After this, we know how to solve x1, x2. Do Gaussian elimination here. So once you do Gaussian, so take this on the left side, this on the right side, and then just find out what's going to be the Gaussian elimination. So Gaussian elimination, say I know how to find the null space vector. So the second step is going to be pretty straightforward. But usually they don't ask eigenvectors. I have never in my life seen anybody asking eigenvectors. They only ask eigenvalues. Because if you know how to find eigenvalues, you know how to do eigenvalues, eigenvectors. So you just find eigenvectors, so that's going to be sufficient. Sorry, eigenvalues, that's going to be sufficient. But for every eigenvalue, there's going to be a corresponding eigen. Now, you can even have it in 3 cross 3 matrix format. So just put minus lambda everywhere. You'll get a cubic. You solve that cubic and you'll get 3 solutions to that cubic. So that's going to be your 3 eigen values. All right. Eigenvalues, eigenvectors, very easy. Just do minus lambda thing, solve the quadratic, get it. They'll never give you cubic also. I've never seen them give cubic. Max to max quadratic. That is the maximum they give. Okay. But maybe they ask you some questions on it, that let's say A minus lambda I is, what is the rank of A minus lambda I? Okay, so the rank of A minus lambda I, since X is non-zero, A minus lambda I cannot be full rank, so it has to be strictly less than N. Okay, so they can ask you some questions based on this particular analytical things about A minus lambda I. So remember, the key thing here is that x is non-zero. X equals to 0 is not allowed, which leads to the other sections. Okay, so I've already laid down the homework for you. It is the second problem set and the past year papers. Okay. So let's, so this wraps up linear algebra.